Hey everybody, Mrs. Bodechon here. So this is AKS 8D. It says I can use mathematics and computational thinking to identify the relationship between work, mechanical advantage, and simple machines, calculate and give examples of the force distance trade-off that occurs when a machine is used. So let's look at your portfolio. You're going to see a series of pictures that look like this, and it asks you a whole bunch of questions about them, so let's go over them one by one. First thing we need to know is what is work? So work is a measure of energy that occurs when an object is moved over a distance by a force in the same direction as the motion of the object. So let's look at the first example. We have a woman pushing a box, okay? So the direction of her force, the way that she's actually pushing it, is forward. And the direction that the box is moving is also forward. So if your direction of the force and the direction of the object's motion is in the same way, you are doing work. Okay, so this isn't like, oh, I go to my job and I do work. That's not this. Okay, this is we have an applied force in a direction is the same direction as the object moving, then that is considered work. So if we look at the second scenario, we have a girl walking and she has her backpack on. Well, when you have your backpack on, your force is up because you're holding the backpack up against gravity, okay? But you're walking forward. So these are not the same direction, up and forward, right? So this is not work. If we look at this third scenario, we have a lady picking up a bag of groceries. Your force then is up because you're pulling the bag upwards, and the direction of the bag is going up. Because they're going in the same direction, this is considered work. Our fourth and final example is the lady carrying the bag of groceries into her house, right? In this case, we're still holding the bag up against gravity because otherwise it would fall down, right? But we're moving forward, right? We're walking forward, moving forward, so the bag is moving forward. Because these are not the same direction, no work is being done in this example. So what is our equation for work? Work equals force times distance, or FD, okay? Force times distance. So is work being done in the following examples? We went over those. If a man pushes a block 10 meters with a force of 20 newtons, how much work is being done? All you have to do is multiply. It really is that simple. So newtons is going to be our force. Force is measured in newtons, okay? And meters is a unit of distance. So 20 newtons times 10 meters equals 200, and our unit for work is joules. Joules, you remember we also measured from energy. Energy was joules. Work is a form of energy, okay? So it's also going to be joules. This next one says, a mother carries her 10 Newton baby from the kitchen to the living room 15 meters. How much work is being done and why? So there's no work being done. And I know that sounds crazy because it seems like it's going to be a big math problem, right? And it's not. You need to really think through this for a second. The force is not the same as the direction of motion of the object. Therefore, no work is being done. It would kind of be like the lady carrying groceries, except she's carrying a baby, right? So her force is up, holding the baby up against gravity, but she's moving forward. So it's not the same direction. You don't even have to do math there because no work is being done. Now, on your sheet, you have this example, and this is the force distance trade-off. It says 3 points, A, B, and C, right? This is kind of like a mountain, kind of picture as a mountain, okay? Point C represents the peak of the mountain. Runners at point A and B race to the top. Which runner exerts a greater force, and which runner does the most work, and explain why, okay? So here we go. They actually are doing the same amount of work due to the force distance trade-off, which sounds crazy, but I'm going to explain it. So the climber, which is this one right here, right? The climber goes a shorter distance, but uses a lot of force to climb straight up. So they're definitely applying more force, but because they're applying more force, they get to do it over a shorter distance, okay? The hiker, which is this one over here, has to cover a longer distance, but uses a very little amount of force. So they end up being the same amount of work in the end, because remember, it's just force times distance, and it is a trade-off. You're either going to do more force or you're going to go a greater distance, and you get to pick which one you do for your work, all right? Okay, now you're going to have this table in your AKS portfolio to complete. We are going to go over each simple machine. I'm going to show you a picture of the models, and we're going to go over examples of each one, okay? The first one is a lever, okay? And the lever makes lifting weight easier by using a fulcrum to redirect force over a longer distance. So examples would be seesaws, dump trucks, a broom, like right here, like sweeping, crane arm, hammer claw, crowbar, fishing pole, screwdriver, bottle opener. You guys, there's a lot of different examples for a lever, obviously, but pretty much just anything with a fixed point, like the fulcrum right here, and the rest is going to teeter, right? It's going to teeter, which is why a teeter-totter is a great example, like the seesaw, okay? You push down on one side, and the load will go up on the other side, all right? A pulley, let me see if I can move this. There we go. So a pulley is a simple machine consisting of a grooved wheel that holds a rope or cable. Great examples, flagpole, the elevator, that's how the elevator goes up and down with a pulley system, sails on a sailboat, fishing nets, clothesline cranes, window shades and blinds, that's how you get the blinds to go up and down, right? Rock climbing gear. So you guys can see the pulleys that are on here, okay? And there's lots of different types of pulleys. But just know some really good examples of those. Wheel and axle. Move this up here for a second. So the wheel and axle is a simple machine consisting of a large wheel rigidly secured to a smaller wheel or shaft called an axle. Okay, so we have a wheel and an axle, and this one's pretty straightforward. This is just going to be anything that pretty much has a wheel, right? But it goes a little bit farther than that as well. So like cars have wheels, bicycles have wheels, office chairs, they have the rollers on the bottom, right? A wheelbarrow has a wheel and axle system, shopping carts, hand trucks, roller skates, but think bigger. Think like a Ferris wheel is also wheels, and a doorknob, right? The doorknob has a wheel and axle system which you can turn as well. Inclined plane. So an inclined plane is an even sloping surface. And I know you're thinking that like even sloping, but yet I see some stairs here. That's not even, but it is an incline, okay? So definitely think of it as that as well. So examples, a highway or a sidewalk ramp, stairs, incline conveyor belt, switchback roads, trails, anything like a ramp, right? To get from a lower point to a higher point, you have that ramp to go on as well. Wedges, show you this right here. Let's see. A wedge is a double inclined plane that moves. So we're taking two inclined planes, we're putting it together, and we're moving it, okay? So an axe, a doorstop, we wedge it in the door so the door won't close. Chisel for like chiseling wood. Nails, saw, jackhammer, bulldozer, snowplow, horseplow. Zipper. Zipper is interesting because everybody's like, whoa, a zipper's not sharp. It's not, cutting through things, but a zipper does pull things apart, right? And that's part of the definition. So just make sure you understand that it does actually pull things apart. Scissors, because it does cut, it does have a wedge that will wedge paper and whatnot apart. Airplanes, although you don't think of it as cutting things apart, same thing with like the bow of a boat. When we're talking about airplanes and the bow of a boat, we're talking about the beginning, like the actual tip of it, right? An airplane will cut through the air. A bow of a boat will cut through the water, so it does wedge its way through. And a screw is the last one, and you can see some different examples of screw here. So screw is also a modified version of an inclined plane. We're actually taking an inclined plane, as you can see right here, and we're just wrapping around like a cylinder. It's one really good example of how to make a screw. So you can see just a normal screw is a screw. A lid jar is a screw. Drill bits. We have like a screw slide, the top of bottles, right? The actual bottle cap. These really fun pinball machines have screw machines, right? A spiral staircase, screws for screwing in a light bulb, and then the top of a pickle jar. Really good examples. So I'm going to stop here, and I'm going to talk about mechanical advantage in the next video.